Okay, good morning and welcome to our sixth and final Saturday physics lecture of the fall. This is our last one in the fall term. We thank all of you for participating. How many people this is their first time to come to a Saturday lecture? Yay! How many folks have been here more than once this fall? Yay! Wow, that's great. How many people have been here 5 times? Wow, look at that. How many people have been to all 6? All right. Thank you for coming. Thank you for coming. We hope you enjoyed the term. Before we get started today, I just have a few announcements, and I also want to thank a few of the people who make these possible. These are a lot of fun for the folks who put them together. And I think they're a lot of fun. I hope they're a lot of fun for the folks who come to see these talks. First of all, the person who does all of the organizational work and makes sure that everything comes together is Tony Pitts. She's right there in the back of the room. Let's give her a big round of applause. Tony keeps the webpage up to date. She makes sure that you all get email notifications when you sign up. She makes sure that we know that you are here, and it enables us to keep track and also to keep you posted, teachers in particular, of upcoming activities. We really appreciate all of her work. The real brains behind the operation is Inga Carliner, and she's back there also. She's the one who does She's thinking about speakers for next fall, so you know that she's the one who actually really makes this thing tick from the standpoint of planning and getting the great speakers that we have. A few other people that I want to acknowledge quickly. Those of you who come regularly know that we see a lot of cool demonstrations, and you're going to see some really cool demonstrations today. Mary Evans and Gwendolyn Bragg do a lot of work setting these things up, and we really appreciate their work. Bernie Dick and Erica Smith, they also help with the preparation, and they're putting these things on video. And I promise you, one of these days we're going to have the ability for folks to see these things on DVD. It's in the works. So thank them for their work. Physics Society, undergraduate physics majors here at the university also help a lot with the setup, and they're around here for all the program. I don't know where everybody is at now. Some of the guys are over here, and we really thank them for showing up every single Saturday. As far as a college student goes, 10:15 on Saturday is dawn, and we appreciate them coming in on Saturdays and helping us out. Now, in case you haven't gotten enough physics during the fall term, there's actually more in the spring. And I apologize, it's a little hard to read because we didn't get it's a little hard to get the transparency up. But there's a program in the spring called the Saturday Astrophysics Program, and there'll be more information on the web very soon. Actually, it's at an adjacent website to our Saturday Physics Honors website. But there are lectures scheduled for February 5th. February 19th and March 5th right here in this room. And so if you're interested in continuing the momentum of seeing some very interesting, very fascinating talks in the spring term, those will be coming soon to a physics demonstration lecture area near you, namely this one. Okay? So we're looking forward to that in the spring. Okay, finally, you've seen all these cool apparatus, and I'm standing here making you clap for everybody, so we can get on with the show. Professor Jim Eckstein came here from industry. He came here from Barrio research in California, where he worked for a number of years and is a real pioneer in the field of thin films, and that's what he's going to tell us about today. I asked him, he has a very interesting background in how he got involved in physics. And so especially for the high school students, I thought it would be interesting for him to just say a few words about how he got into physics. I think it's an interesting story. And so I'm going to spare you a lot of the kudos, and he's got articles published in a lot of very prestigious journals, Science and Nature and things like that, a number of awards and things. So he's a very top researcher in his field. He's also an excellent speaker, and we're really looking forward to hear from him. And as I said, we appreciate him telling us a little bit about his background. So please welcome Professor Jim Eckstein.
So Kevin asked me to just say a couple of things about how I got into physics, and maybe it is a little unusual because I went off to college thinking I was going to be an English major, and English and humanities, and I spent the first year really enjoying that and studying history and literature and things like that. But at the same time, I had a really cool freshman seminar led by a physics professor, and that got me thinking just about the philosophy of how do you know things, what does it mean to know something, theories, how do theories change, and things like this. And that sort of bubbled around for another year. And then by the time I became a junior in college, I decided this just was just too good to pass up for my life, I guess. And I switched over to physics, and I managed to get it done in 4 years. It was a little rushed at the end, but it's definitely the case. And I'm certainly a firm believer that you want to do what you want. You want to take a good assessment sort of at all times about what's really interesting you, what's going to keep you excited in your mind. You know, what you're doing is going to be what you really want to do. And I found that out sort of in an evolutionary manner. And as you go on, those of you who are in high school now, off to college, just keep an eye on that. And if you decide that you're maybe not on the right track, then evolve. You don't have to worry about being too late. Certainly wasn't too late for me anyway, but from English to business. I can't spell now, that's my problem. Anyway, so I'm going to talk to you about, the title of my talk here is Making Crystals That Nature Cannot Make, and I have a lot of collaborators, and I'm going to show you their pictures at the end, actually throughout the talk as well, but even some people in this room that are going to have their pictures up on the board, on the screen here in a moment as well. It's great to see a lot of young faces, and it's great to see some other faces that I'm sure are not quite high school age, like right there, and a few others in the room, and I'm glad to have you all here. Okay, so nature does make crystals. I'm going to talk in the end about things that nature doesn't make, but let's just sort of set the stage about what goes on when this occurs, when crystals are formed. These are some examples of naturally occurring lasers. This is a crystal that a picture I got off the web of a crystal of lead sulfide. It's also known as galena, and this kind of stuff you can just naturally pick out of the ground, I guess. I have never done that in places like Galena, Illinois. This is a semiconductor material, and you can see just by nature itself forms these cubic structures here that are pretty darn close to being good single crystals of lead sulfide. Likewise, materials like rutile here, it's a form of oxidized titanium, also naturally formed. And here's a couple others. This is a form of fluoridated calcium that's known as fluorite, and it also naturally forms. You see these very nice crystalline rectangular structures here. There's more than one grain in this crystal present, but there aren't too many of them. There's just zillions and zillions of atoms involved in each of these rather large crystallites here. This is a crystal here of a bunch of crystals of quartz that are found inside a geode. This is just one that we happen to have next to the fireplace in our house. And this is kind of an interesting thing. These crystals of quartz formed over eons of time when water vapor carrying silicon dioxide infused through holes in, I believe, in volcanic materials. This took an incredible length of time to form. It's a naturally occurring crystal, and it's formed by the mechanism that I'm going to describe in a moment that nature uses to make crystals. You can also use this same process to make your own crystals, and I did this while we were cooking Thanksgiving dinner. I started it out. This was just a crystal that I'm growing here of actually sugar. Here I dissolved a lot of material, a lot of both sodium chloride and sugar in 2 different beakers, and put, so you see that right here. If you look up closely at this point right here, just as I was starting, you can just barely see at that point right there where I rubber cemented a little grain or a couple of grains of sugar onto the end of a sewing needle here. And then I waited a long time, about 2 weeks, and a lot of water evaporated. And look what happened. I grew these nice crystals that seemed to grow out of the grains that I started with. At least some of them did. And these are substantially large crystals, maybe about a centimeter inside. So this is what had to happen. What actually is happening in detail, and why is it occurring? That's what I wanted to start talking about. What really controls how do crystals grow? Well, all these crystals are made up of atoms or molecules, and those atoms and molecules are in the solutions from which the crystals grow. The atoms and molecules like to form bonds, and the nature of the bonding that's formed is really governed in large part by the structure of by the kind of atoms that are present. These here are models that show you what the electron distribution is like around involving different kinds of what are called electron orbitals. These are the kind of states that electrons can be in. These represent the states. These are wooden. I mean, the states that electrons in aren't wooden. They're tiny little things about an angstrom in size. But this is a representation of, for example, an S state of, maybe you remember this from chemistry, that an electron can be in. This is a representation here of a P state. This is a representation of a certain type of state called a D state. There's another D state right here, and a third type of a D state right here. So these things, these electron states have a geometrical structure to them, and that geometrical structure is very important in determining what the ultimate shape and nature of the crystal that can grow is. So it's these atomic orbital geometries that at least in part, lead to the crystal symmetry. Now, besides the fact that they've got this structural symmetry to them, these orbitals, what happens is the atoms that are making up a crystal join together in something called a unit cell that stack together essentially like Lego blocks. So these things come together in units, these unit cell units, and they result in large samples that have symmetries that are sort of controlled by that. Here's just some computer pictures of how that can look in certain cases. This is a crystal of the kind that I'm going to be talking about today. It's got a structure that's known as perovskite. You don't need to remember that name, but it's got a type of atom here in the middle that's got orbitals that look like this and like this, and together they provide sort of a rectangular Cartesian structure in the center of this. That's this red atom here that come out and bind to the blue oxygen atoms, and the shape of these orbitals is also indicated right here. These are the ones that I'm talking about right now. So let's just talk a moment about chemical bonding. Here's the sequence of three atoms here, a manganese atom, an oxygen atom, and another manganese atom. And this oxygen atom here has got three of these p orbitals. Here's this blue one here, this sort of light pink one here, and this darker pink one there. And it's neighboring here to two manganese atoms that have d orbitals that are pointing in these directions. As I was saying before, these atomic orbitals have a geometrical shape. The orbitals obviously can overlap to some degree, and the secret to what happens is understanding what happens when these orbitals do overlap. If this is done properly, then the energy of that configuration is lower. If the energy is lower, it's bonding. Okay? So the bigger this energy decrease, the more stable the bond is, and the more tightly bonded the atoms are. Now, you can draw a sketch here of what goes on when you bring, say, this atom close to that atom right there, and these orbitals overlap. The question is, how does the bond energy, how does the total energy, I should say, depend on the separation? And what it looks like is like this. It's a curve that is kind of very sharply rising when the atoms get too close together. You try to bring them too close together, they really repel each other. They don't like that. There's a strong repulsion that's due to the positive charge in the nucleus of this guy seeing the positive charge in the nucleus of that guy. And that doesn't let them get that close together. That's why this curve is rising so rapidly here. On the other hand, when you're far apart, there's essentially no energy that there's no advantage or disadvantage to the energies that the atoms have. But in between, in this region right here, there's a slight advantage to being having the atom at the atoms at that separation. And if you just measure this, this is just the right separation, and this energy benefit that you get relative to having the atoms completely separated from each other is the bonding energy that holds this bond together here. So that's the nature of bonding, but there's more to it than that, because you could ask the question, if bonding always lowers energy, then isn't it always favorable? Why is it the case that sometimes when you are growing a crystal, for instance, when I was doing that in my kitchen, why did I have to have some water evaporate before this would start to happen? Why did I have to reach this so-called saturation? The answer to that, I think we can get by looking at what I've got in the next couple of slides here. imagine we have this little beaker here full of water and some atoms in here, and this is the crystal. If you have not enough atoms in the solution here and a lot of atoms in this crystal, an atom leaving the crystal surface is essentially just going to get lost. It's going to leave the crystal and diffuse out into the solution here, and it's going to get lost. And if there aren't enough atoms in that solution, then there's not much of a chance that another atom is going to come and take the place of the first atom before yet another atom leaves. So this process of, this phenomena here of atoms getting lost in the solution here is something that we have to deal with. Okay? Somehow we need to account for that. So to do that, we have to ask the question, we should ask the question, how lost can an atom get? And this is something that you can look at, and we have to remember that in a solution like this, all the atoms are identical atoms. In other words, this atom is no different than that atom. So we're not going to say this atom is lost in this entire vessel, because there's actually 4 identical atoms that are lost in that entire vessel. And because of that, because all the atoms behave the same way, when we count the degree to which an atom is lost, we have to take into account the fact that there's more than one atom present in some volume here. We've got 4 atoms present. If I draw a grid here that indicates what are essentially independent places for the atom to be, I end up with 144 spots right here in this 2-dimensional array here, and I've got 4 atoms. That means that each atom has got essentially about 36 distinct locations. 4 atoms divided into 144 sites gives me about 36 different places an atom can be. So that's what I mean by how lost an atom can get. You have to take into account the sort of identical aspect of all these atoms when you do this kind of a thinking. Now, the key point that I'm trying to get at here is that we have to not only think about energy, we've got to think about a new quantity that somehow quantifies how lost something can get. And that new quantity is this quantity of entropy. And I want to describe to you what that is. Okay. Spontaneously, systems like to lower their energy. If I have a mass and I drop it, that mass is going to lower its potential energy by dropping into my hand that was down below it. So in general, systems like to lower their energy. Spontaneously, it's also true that things like to get lost if they can get lost. They don't organize themselves into a particular location in space unless there's something more going on than just free atoms in a solution, for example. So there's got to be a trade-off between these two phenomena. One of these phenomena, namely this bond energy phenomena here, is wanting to organize things into crystals, into having chemical bonds. On the other hand, there's this other phenomena here, which is entropy, which is trying to working the other way, getting things lost. And so there's a trade-off between these two incompatible tendencies, and that's what I want to describe to you sort of briefly right now. Entropy quantifies how lost an atom is in a particular situation. In a crystal, it's essentially 0, and in the solution, it's big. Now, how do we deal with this, and how does this really work out? This slide here is going to have the only equations, and I think the only equations in my entire talk. And I want to at least just show you what these quantities look like, but we can still talk about them, I think, intuitively without getting bogged down in formulas and detail. If you've got a system in which you've got an atom that can get lost, and you count the number of ways that atom can get lost. We did that in that previous slide. If you take that number and you take the natural logarithm of that, and the natural logarithm of the number is about 2.3 times the log to the base 10, and then you multiply it times this number right here, which I'll tell you about in a minute, you get a quantity that is the entropy per atom in that situation. Entropy per atom in that situation. So log base, the natural log of 10 is 2.3, the natural log of 100 is 4.6. Natural log counts orders of magnitude here. So you can see as you go up by orders of magnitude, all you're doing is just doubling the log here. And natural log of a million here is only 13.8. So that gives you an idea about how the magnitude of the number of of ways to be lost has to increase in order for this number to get very big. In the previous example that I showed you before, that quantity would be kb times the log of 36, which is some number. What is kb? Well, kb is a number that's known as Boltzmann's constant here, and it's got this unit. It's got this magnitude here, 1.4 to the 10 minus 23 joules per degree Kelvin. Okay, so let's just think about those units for a minute. If I wanted to compare bond energies with something that's got entropy involved in it, bond energies are going to be measured in units of energy or joules, okay? So it's interesting that this quantity right here, which is the dimensions of entropy, has got units of joules per degree Kelvin. So it looks like if we just take this quantity right here, the entropy, and multiply it times the temperature, you're going to get a quantity that is got units of joules and something that we can directly compare with bond energies to help us sort out this tension between bond organization and entropy disorganization that's happening here. So that's in fact what you want to do. How does the energy cost of a certain configuration compare with the entropy gain of that configuration, which is just its temperature times the entropy quantity. So there it is. This is the thing we want to compare. Temperature in units of Kelvin times this quantity right here times the log of the number of ways you can be lost in that particular situation versus the energy when you're not lost. Okay, when you're bonded up, for example. So here's the way this balance works out. When the temperature of the entropy is low enough, when this is small enough, or this quantity right here is small enough, then this is smaller than that, and it's better for the atoms to join the crystal because they're not paying much entropy price for doing that. On the other hand, when these things here are big, then it's much easier it's much better off for the atoms not to join the crystal and dissolve into the liquid. So that is that's something that is we can actually let me just step back here for a minute. We can actually get an idea of entropy in several situations here. I've got several demonstrations right now that I want to show you that describe how entropy controls certain phenomena. If I have a deck of cards here, and I organize this deck of cards from, the 2 of whatever diamonds to the ace of spades at the top. So I put it in a configuration that is maybe the standard best configuration for an organized set of cards, and I ask what's the entropy of that. Well, I get a number like 0, because that's the one configuration that has everything organized in an ascending order. If I do this, which I can do because I'm not going to clean it up, it's all a mess, right? How many different ways could I do this? I could do this many, many, many different ways. And if I could enumerate all those ways and count them up, I'd have something that I could take a log of, and that would give me something like the entropy of the situation. This is kind of an absurd example. There are others that are I think a little more easy to comprehend in terms of atoms and so forth. And here's an interesting one. I've got some dye here. I guess I have more than I thought I was going to have. I'll put it on the slide. This looks like a few, what is this about? 30 milliliters, 40 milliliters, 50 milliliters, and I've got 3,500 milliliters of solution right here. And if I gently pour this in to here, I can't pour it in as gently as I would like anyway. But even if I could, what would happen is that after a period of time, you'd see the atoms diffuse around, the molecules rather, that are these green dye molecules diffuse around, and this thing here is just going to become uniformly light green. And it's doing that because there's no penalty for being disorganized. In this case right here, we're not really breaking any bonds apart. In this case here, what's happening is the system is evolving towards the most disordered situation it can possibly find itself in. It increases its entropy by a quantity that's kind of like what I indicated up here. The final volume divided by the initial volume. Instead of it being what I had guessed here, 0.02 milliliters divided by 100 milliliters, it's actually some different numbers. But it's going to be something not too different from this because of this disorganization that's happening. there's other cases that are also interesting that we can look at. Here's one in which we start with liquid nitrogen right here. And let's see if I can do this right here. I can pour this liquid nitrogen into, and so the liquid nitrogen's got lots of nitrogen molecules, N2 molecules that are very close to one another. They're just in a liquid form. And I'm going to pour them into this metal cylinder right here. Pop it off here. Spitting out. Well, try that again. So I got to really whack it. Okay, thank you, Anthony. So what was going on there in terms of entropy? What was going on here in terms of entropy was that the atoms, when they were in the liquid state, molecules when they were in the liquid state had a much lower entropy than they did when they were had vaporized. And at the temperature where you convert from being a liquid to being a vapor, you get a tremendous gain in this Kb times the log of the number of ways in which the atom can be when it becomes a vapor, because all those nitrogen atoms, molecules rather, are just they're just dispersed throughout the air. There's many different places for them to be, so that becomes a very good number, and it's a force to it leads to that expansion, and that was enough to blow the torque off. Now you can get similar kinds of phenomena in other kinds of cannons, but most of them also involve some large increase in entropy. It is possible to have cannons in which you don't have any increase in entropy, like this one right here. This is one of my favorite ones. But this one is a case where you're getting that projectile set in motion without having any change in the entropy. So you have to be careful. Not all cannons involve entropy. The last example that I wanted to show you here is this one right here. We put the camera on the scale. Here what I have is a rubber band right here. The rubber band is holding a mass up. You can't really see the rubber band too well. It's going all the way up to the top. It's about 1.5 feet long. Here's the mass. And right now the rubber band is in a condition that I would call cold. Okay? Now, let's just take a look at what the rubber band is made of. The rubber band is a polymer, and it consists of molecular connections that can either be all pointed in the same direction, like that right-hand image is right there, or in situations where sometimes they're pointed in the same direction as the neighbors and sometimes they're pointed in an opposite direction. And when that happens, when this thing here happens, then it's shorter, right? Because the total length you have here, when they're all pointing in the same direction here, is as long as it can be. So now, so this is what we've got going right here. Now let's ask the question, which configuration has more entropy? Now, in this case, we're not really getting a loss, but there's some sense there's disorder present in this situation here. Here we have all these bonds pointing in the same direction. Here we've got them alternating sometimes. Sometimes they're pointing in the same direction, sometimes they're alternating. This one right here, the one with more disorder here is the one that's got the larger amount of entropy rather. There's many ways in which that can happen. And in this limiting case right here, there's only one way. Well, you could imagine that the longer you have this thing stretched out, the lower the entropy is. That's the safe thing to say here about this in any case. So you can ask the question then, what happens if we heat up the rubber band? Okay, we have this rubber band that's stretched out like this. Maybe not exactly like this, but still it's in a stretched out configuration. What do you think is going to happen? Is nothing going to happen? Is it going to get longer, or is it going to get shorter? So who says nothing's going to happen? Good. All right. Who says it's going to get longer? Okay. Who says it's going to get shorter? Okay. Let's find out. Okay. Now what I gotta do is, I'm gonna turn this lamp on, and this lamp is gonna keep the rubber band up. And you're gonna have to look right here. You can see where this is right now. It's just a tad above this little line right there, right? So when I turn this light on, I've got to actually change the f-stop of this camera because the lights change illumination. But I'll do that. But remember where we are right here. We're a little bit below the 65 mark, I guess, right? We're between the 65 and 64 mark. Okay, so now we're up to 66. So look, it's getting shorter. Isn't that weird? That's really interesting. That's a great demonstration. What's behind this is entropy. Okay, and let me show you why. In fact, let me do one more thing now. Let me turn the lights off, and you'll see the thing come back down as it cools off. It gets short. Okay, so what's going on here? Well, when we add temperature to this situation, when we increase the temperature of that system that can have disorder in it, the disordered states, the more disordered states can take advantage of that temperature increase because remember, the quantity that we said has to be compared with the cost of doing something. The cost of doing things right now is raising that mass up, because that you have to do work on that mass. Raising it up takes some energy, right? How do you balance that out? Well, you balance that out because as you increase the temperature, the states that have larger entropy can benefit enough to lift the mass up. So the trade-off works in the favor of the states that have more entropy. And that is what's responsible here for the hot rubber band lifting the mass up. Okay. It's a different trade-off between entropy and energy that's happening there. So these are interesting cases. These are interesting examples, demos, that show how entropy can control the way things happen. It's true that entropy is almost as important as bonding energies and the energy things that I talked about at the beginning of my talk in controlling how crystals grow. In particular, that's the case when we're growing crystals in what's called equilibrium. Okay? And everything I've talked about so far, where we're dealing with this trade-off between energy and entropy, is essentially what we call thermodynamic equilibrium. And generally that's good. As a practical matter, this is one of the ways you can get extremely high-quality crystals, not many defects. And the reason for that is that during the process of growing a crystal this way, like in my kitchen when we were growing those sugar crystals, each atom can try many times to find the best spot to be, and it can only settle into a spot when it's found really the very best place for it to be. So that's one of the reasons why thermodynamic equilibrium is such a good way of doing things like this. However, there's lots of reasons why you might want to do things different, and what we do in our lab is try to cheat Mother Nature. Okay, can we do that? Yeah, but don't tell her, right? So what we want to do is not be too far away from chemical equilibrium, but what we're going to do is we're going to control the supply of atoms as we grow crystals. Okay, we're going to circumvent most of the effects of, we're going to get rid of most of the effects of entropy, at least many of the effects of entropy that we've been talking about, and that's going to allow us to grow structures where we manually sequence a stack of atoms and get artificial crystal structures in that manner. Okay. Why is this good? Well, what I'm going to show you about today, I'm going to show you today is some data on some samples that we've made where the samples have brand new properties that didn't exist without doing the kind of artificial synthesis that we've done. And so we can make materials that have new properties. We can also make devices this way. And in fact, many devices are made far from thermodynamic equilibrium as well. So that's not something that is only something that we do. It's something that is actually fairly common. All right, so I'm going to talk about oxides, and the kind of oxides that I'm going to talk about, these are the crystals that we're growing, are sometimes referred to as complex oxides, and they are a little complex, but not too complex. I'll try to walk you through what's going on here. These crystals have a form that's typically shown like this, where we've got atoms that are either yellow here or green down here in these cartoons that are bonded to oxygen atoms, which are the light blue atoms, like this. And then in the middle of these cages, you find atoms, either this purple atom here or that red atom there, or if you try to join this unit cell here with this unit cell, perhaps this blue atom right there, that are bonded in a different manner than these smaller atoms are. Most of the real business involved in understanding how these things behave is controlled by the nature of what this yellow atom is here and how it connects to the oxygen atoms around it, or the nature of this green atom here. You could have whether you get out a magnetic material or a superconductor or other things. I've listed some of them right here. Just depends on, in many respects anyway, depends mainly on what's the nature of that atom that we're putting in there. Okay, and the chemical formula for what these atoms, for these molecules here is something ABO3, and the BO3 bands, the BO3 states are the ones that really control what's going on. So it's the same before. Okay, actually what I want to do now is just skip to the slide here that shows us how do we accomplish this. Okay, what we do is when we make our crystals this way is a process known as atomic layer by layer molecular beam epitaxy. And we have a vacuum system right here that is a good ultra-high vacuum system. And inside this vacuum system, we've got lots and lots of different sources. In fact, we've got 12 different metal sources right here. Copper, manganese, titanium, aluminum, we have nickel in there. So all of these different sources. Plus we have a source of very reactive oxygen. It's called ozone. It's O3. And O3 is almost as reactive as atomic oxygen. It's easy to pipe around. You can pipe ozone around in stainless steel tubes and in Teflon tubes and so forth without having it decompose. And we just bleed a little bit of ozone in front of where we place our substrate. Now I forgot to mention something. I think I'm going to mention it to you in the next slide. We do our crystal growth on top of something called a substrate. Well, let me just hold off on describing that to you until we get to the next slide. That's sitting right here, and we open and close shutters and sequence the supply of atoms. And if we do this accurately enough, we can open this, say, strontium shutter up here for just the right length of time to deposit one atomic layer of strontium oxide. And then we can shut the shutter and then go on to the next thing that we want to do. And in that manner, we can artificially stack up the crystal structure that we want to grow. And we're not stuck then with how Mother Nature makes that trade-off between entropy and energy. We don't have entropy present in nearly the same way as we do in thermodynamic equilibrium. Okay, let me just see the next slide. Oh, the next slide is a picture of the system. That's a picture of the side of it. And that's a picture of the end of it. And I think the next thing we're going to do is we're going to go down to my lab and take a look at what the system looks like and get a little tour of the system. We're going to be talking to Maitri here, who's maybe on the speakerphone right now. Let me see if he's there. Maitri?
Hello?
Oh, there you are.
Oh, hi, Jim.
Yeah. We're going to try to get you on the screen. We don't have you up just yet. How's the crystal growing going today?
We are going to grow a superconducting viscofilm and we are getting things ready here.
Okay.
And I guess you want to see our chamber.
Oh. Yeah. There we go. Yeah.
Can you see it on the video?
There you are. The screensaver was on, and you weren't coming through, but we figured that out, and actually Gwendolyn figured it out. Okay, so do you want to give us your tour?
Yeah, what we could do is we could show everyone what our chamber is like. It's a big, huge, gigantic machine. If you can see what the machine looks like, it's like an anchor for a ship. So what this big putting film on a really small, like a small sample. And what we'll do is, if you can show them what the where we mount the sample. Okay, if you can see that, that's the puck that we mount our sample on.
There's no sample present in
It's
that.
about 1 inch in diameter, and a sample that's about 1 centimeter square would go in that. And what we do is we have to get it into this chamber. Now the chamber sits at very low pressure, so we do that. We have actually 3 chambers. I'll try to walk you through that. What we have right here are transfer rods. These rods help us transfer the sample from one chamber to the other, and over here, this is the load lock chamber, and all that the only part of this whole chamber that sees atmospheric pressure is this little load lock chamber. So the sample will be inserted in here and transferred through with the transfer rod into this middle chamber and then into this big main chamber. Can you see the main chamber there?
Yeah.
Okay. The base pressure inside this main chamber is around a trillionth of an atmosphere. So that's very low vacuum. In fact, we call it ultra high vacuum. Now, actually, we have a substrate, a sample that's inside this chamber that we transferred just a little while ago for today's growth. And what I'm going to do is to turn this substrate to face forward. Let me try to do that right now. And here, I'm turning it forward, and I think I've got it there. So, what does this substrate see when it's faced forward? It sees this source plane. Now, maybe Jim can point everyone where our furnaces are. So we have 12 different furnaces on the source plane, and each furnace has some material, and the material is actually kept inside a crucible. If you can see this is a crucible that came out of the chamber. It's the old crucible that we used to have copper inside. So we have all these different crucibles and furnaces, and these furnaces the temperature of these furnaces are controlled by pretty precisely. And so the furnaces sit at very high temperatures, and when we heat these crucibles up with an element, the crucible starts throwing out atoms at some particular rate that we have to very carefully calibrate. What we'll show is we'll show you a temperature controller. If you can see this temperature controller unit is actually controlling the temperature of the copper furnace, and it's at 1090 degrees C, 1090 degrees centigrade. And that's the temperature we want the copper crucible to have for today's film. The other thing that we should show everyone is that we have shutters in front of all these furnaces, which allows us to open and close the shutters, and by that way we can control how many atoms actually hit the sample surface. And we do that by using a computer. Let's show the computer screen here. We have right now a computer screen that's set up to grow a visco film, and I wonder whether everyone can see numbers in there. What we do is we feed some numbers into the computer, which tells the computer exactly how long it should open a shutter and keep it open to deposit, say, exactly a monolayer or a fraction of a monolayer. And maybe Jim might be able to point out the numbers and tell everyone what we're trying to do here.
Okay, Mikey, should I do that right now? I guess he wants me to do that. So here, this is a sequence of steps. And the first step here would be to deposit one atom per unit cell of whatever this column here is controlling. And it says dysprosium, but it might be hooked up differently. And then the next step in the sequence is to do 0.55 unit cells of whatever this atom is, and 1 unit cell of whatever this atom is, and then so forth and so on. So you can build up whatever you want by simply going in here and putting in the numbers for what fraction of a unit cell coverage you want each step to give you. What this relies on is having very good numbers here in this row right here, which tells you how many atoms are coming out per square centimeter per second. And then that calculates how long the beam shutter should be open. And the shutter's open for that length of time. We think at that point the shutter, the system deposits 1 unit, whatever we ask for, and then the shutter closes. So that's the sequence. That's an interesting looking recipe there, Maitri.
Yeah. So I think the last thing that we could maybe show is a diffraction image of a crystal. If you could point the camera at the reed, we have to turn off the lights here to see this. So let me try to do this right now. Most of these experiments are done in the dark. And get that light off too. Okay. So let me align the reed here. Okay, what you see over here is a real live image of a crystal surface. It's actually a very flat crystal surface. The flatness is on the order of angstroms. This diffraction image allows us to say a lot of things about the crystal. It gives us a lot of information. And the most important thing is that during the growth, we can keep looking at this image, and so we get feedback. If something is going wrong slightly, we can go immediately and adjust that, so we can get a very accurate film. And I think Jim is going to talk more about the read with everyone and discuss some aspects of it at least. So. And at this point, I think, can you see the read screen very well?
Yeah, it's great, Matthew. I think that's probably good enough. I think what we'll do is get on to the rest of the talk and talk about how read works right now, okay?
Okay.
Thanks a lot, Matthew.
No problem.
Good luck today.
Okay, thanks.
Okay, so that worked out. Surprise. So let's talk a little bit about that last thing that we looked at there a moment ago. It's called reflection electron diffraction. And this is a way in which we can get an atom's view, an atomic eye view, right down to the atomic scale of what's going on as we sequence the chemistry to grow these artificial crystals. First of all, the easiest thing to describe to begin with is a diffraction phenomenon that happens in a system that I think everyone would agree is a wave-like system, and that's light. And so what we have right here is a green laser. You can see this green laser here. And behind this green laser is something called a gradient, a diffraction gradient. And it consists of a bunch of regularly spaced grooves in a piece of plastic or glass here that are spaced apart by some spacing. I'm not exactly sure what that is, some number or fraction of some number of microns, I should say. And when a light wave comes into this, light wave comes into this, what happens is that the phenomena of diffraction, and you get some light that comes on that original path like this, but some light goes over here. And the light that comes over here is light that that follows these kind of paths that are shown right in the slide right here. Let's see if oops, I didn't annotate that. I'll talk about that in the next slide when we talk about electron diffraction. But what ends up happening is that if you look at this directly in the same direction that our original beam is coming at, and then you go one spot up, this spot is formed by rays that are coming from each of these holes that are different in their path length by exactly one wavelength. This spot right here comes from rays that come from each of these holes that don't differ at all in their path length. And this spot right here comes from rays that differ in path length by exactly 2 wavelengths, which end up getting is a sequence of spots, and that's these spots right here, that are due to this interference phenomena. This spacing here can be quite small. It's on the order of microns. But the separation that you get here is given by the wavelength of the light that we've got here, which in this case is about a half a micron, divided by the spacing, which is maybe several microns, times the distance right here. And that, if you can measure D, and if you know A, lambda rather, you can find out what A is without measuring anything that's very small, just measuring big things. But you got to know what A is to do this. Sorry, you got to know what lambda is to do this. Okay, let's talk about what happens with electrons now. You can do the same kind of diffraction with electrons, and that's kind of weird because you might think of electrons as being material particles and not waves. But as it turns out, quantum mechanics has something else to say about that. Quantum mechanics says that electrons behave like waves and particles. In fact, this kind of a behavior right here, the fact that the electron has to live in a state like this is ultimately due to that the physics behind that. Back in the 20th century, Barrio showed, a fellow named Barrio, showed a wavelength that's controlled by this equation right here. Oh, that should be h squared. Sorry, it should be h squared. 1v squared, that electron is equal to wavelength squared. And you can solve that then for the wavelength, and you find out that it's equal to that expression right there. And if you plug in numbers, you end up finding out that this wavelength here can be really quite small. This is the beam voltage in volts. So typical voltages that my crew was using in there are probably something like around 7 kilovolts, so 7,000. Take the square root of 7,000, you get something that's on the order of 100, something in that vicinity. So the wavelength of the electron using to do this diffraction phenomena that he had was about 0.1, 0.15. And we have the same kind of thing going on in electron diffraction. We've got electron beam now, a wave-like electron beam coming in and hitting the crystal surface. The crystal surface is a regular array of atoms. So as the electron wave comes in there and hits this regular array of atoms, each of those, when it hits each atom, it radiates out a little bit of itself. And those little bits of itself that interfere in the far field on that screen that he had, and you end up seeing a diffraction pattern because of that. A is typically some number like a few angstroms, maybe 4 angstroms. We can measure D, and we know what lambda is from that formula. We can find out. So this is a way in which you can follow. Not only can we know whether we're messing up and the crystal isn't going right, if we're doing something that we have never done before, we can find out what's going on and measure the spacing between atoms very accurately in real time. Okay, so this is just the same old picture that I had before. Here's the electron gun. Our substrate is sitting right here. The beam comes in like this, the diffraction phenomena happens there, and out here we see this pattern here. And the pattern of spots is due to the same kind of stuff that this is due to here. And if we were to change the energy of the light, sorry, if we were to change the energy of the electron beam, it would be the same as changing the light. Have the same pattern in the crystal, we would just get different spacings. But as long as we know what we've got in terms of the energy, we know what the wavelength is, and we can get back. Now, the kind of crystals, artificial crystals, I'll tell you about today, in the last bit of my talk here, are crystals that are insulators, and they're useful for applications involving electrodynamics. And the kind of things that we'd like them to be useful for are optical applications involving optical communications and maybe even quantum communication, although that's a little bit, that's something we're not sure if it's going to have any application. We know that we can make gizmos out of material like this that allow us to take a laser beam like this, pass it through the gizmo, and change its color a little bit. We don't kill the photons and re-emit them. We just take individual photons and we can shift their wavelength just a little bit. And that's useful because in optical communication systems, many times on a single optical fiber, you'll want to have several different colors of light traveling down in a fiber, each one of which is carrying its own bit of information and its own set of information. And so that's an engineering scheme called wavelength division multiplexing. And being able to change the color of light a little bit is something that will allow us to add an interesting component to wavelength division multiplex communication system. Now, here's the gizmo that we use to do the frequency shifting. It's an electro-optic frequency shifter, and it's given us frequency shiftings of actually more like plus minus 400 gigahertz, which is a substantial bandwidth. And it's this object right here is made out of a material here that's got a certain property that's quantified by this coefficient here, R sub c. It's a rather small number, 30 times 10 to the 12, 3 times 10 to the minus 11 meters per volt, 30 picometers per volt. We'd like to have this be a bigger number because since this frequency shifting here is controlled by how hard you drive it, that's the electric field that we pump in right here to control this, as well as by the materials properties that this thing is made out of. If we could make it out of a more responsive material, then we'd get a larger amount of frequency shifting, and that would be good. This is what we've been able to get with just the device that I showed you on the previous slide here. This is the original spectrum of light, and this is the frequency of the light. And so originally we have a spectrum that is centered right here, and then when we gizmo and we add a certain amount of power here, we can shift it over to this position right here, shift the spectrum, shift the color to, let's see, I'm going to higher frequency, which means a shorter wavelength. And here's even shorter, 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 shorter. We're getting some distortion here not to worry about, but you can see that we can move this about 1, 2, 3, 4, 5, about plus minus 5 line widths, which would mean that we could take this gizmo here would be, this electro-optic frequency shifter would be useful for moving an optical communications channel among, say, 5 to perhaps 10 different values, just different channel numbers. So there's some motivation to find out, is there a way of making this number here bigger? Good idea about how to do that. Turn the power up. Well, that doesn't work. Turn the power up and you blast the thing away. Okay, the better solution is to improve the nonlinear optical material. You want to find a property in a sense that I'll describe to you in a minute that's more asymmetric. Okay, now what we want to do is make these asymmetric materials. They can form naturally in the following material. It's a so-called ferroelectric material, and it will enter an asymmetric state at a low enough temperature, but the material that we were working with itself wasn't ferroelectric, and we're after something that maybe is a little bit better. So what we thought was, let's just grow materials here in which we stack up the composition in some important way in an asymmetric manner, and then see what that gives us. And so that's what I'm going to talk to you about. There are artificial superlattice structures where the lattice is made up of supercells, each one of which has got an internal asymmetric structure, and we stack them up. Okay, and what we're going to make this out of are 3 different titanate phases. The phases have composition, there's perovskite phases that have composition ABO3, and here they are. The first phase is the most complex one here, barium titanate. It by itself is this kind of material known as a ferroelectric, which can become either polarized up or down. Strontium titanate, which has got a lighter element in this spot right here. The A atom is lighter. Because it's lighter, it is not a ferroelectric, but it would really like to be a ferroelectric. It's very close to wanting to be a ferroelectric, to becoming a ferroelectric. And it's a well-known substrate material as well. And the last material that we're going to use in our superlattices here is calcium titanate. And calcium is yet lighter than strontium. And, you know, it's kind of clueless, you know. It just sits there and basically doesn't do much. It just holds its place. Okay? So we've got these 3 different materials that are kind of different. We're going to stack them in a way using our technique that is asymmetric. Now, what do we start with? Well, as I was mentioning to you before, I probably should have showed this slide a little bit earlier. We got to grow this on something. So we start with a substrate of a material that is structurally similar to what we're trying to grow our superlattice out of. And we get that material polished flat, And there's some examples of that would be materials like strontium titanate, silicon, gallium arsenide. You can get these materials, you can buy them, they're very nice and flat. And what you do is you grow layers on top of them, so-called epitaxioid. That means that atoms sit on top of that. So if you grow the first unit cell of that pink material and then the second unit cell of the green material, the atoms that are inside those unit cells just on top of each other. That's what we mean by this word epitaxio. Summary of the kind of structures that we've grown here, where we have broken symmetry. So this material here we call 222 plus, and each supercell consists of this, and then that's repeated maybe 40 or 100 times in a sample. And this is just the same as that other material, but it's upside down. So we call this 222 minus. And this material right here has got the same constituents and the same proportions, but because of the way in which we structured it, there's not this asymmetry. It's a symmetric material. So these two guys here lack inversion symmetry. This one here doesn't. Now, what I'm going to show you right now is what we see in that phenomenon called electron diffraction that I was describing to you a moment ago. This is a picture that's shown at the beginning of the growth of one of these supercells. And what we're seeing here is a trace that shows the intensity of this central spot right here as you grow each unit cell in this structure. When we start out, we have a really nice bright spot, and then when we grow 1/2 unit cell, we get kind of a dim spot right there. And it's a really substantial reduction in the intensity. And then when we finish that unit cell, when we go from a 1/2 unit cell up to 1 unit cell, we get back a nice bright spot again. And we can do that throughout the growth of this entire structure. We always get this kind of a picture when we're halfway through growing a unit cell, and this kind of a picture when we're complete. And if we let it sit for a little while at the end, it gets even a little bit better. We end up with essentially the same thing that we started with right there. So that's what we see using this electron diffraction. We can really watch the phenomena happen. And when we look after the fact, we can use a technique called atomic force microscopy to look at the nature of the surface. And it's really flat. This is a height scale right here of 10 angstroms. And you can see the surface here, 1 micron by 1 micron squared, consists of a bunch of terraces because the substrate hasn't been cut perfectly flat, perfectly square, that are atomically flat, and then the unit cell steps down. So that's exactly what we want to have. Why are we getting these center spot oscillations? Well, the wavelength of the electrons here is about 0.15 angstroms. Halfway through the growth of a unit cell, it's going to look like that, and it's going to scatter a lot. And when you complete that first unit cell, it's going to look like that, and it's going to scatter less. And the same thing's going to happen for the next unit cell after that. So that's the reason you get these center spot oscillations. Now, after we grow these and study them electronically, which I'll describe to you in a minute, one of the other things we've done is in collaboration with Professor Jim Zuo, who's right here in the second row, is we've looked at light using a really powerful microscopy technique called scanning transmission electron microscopy. This is Jim right here and the student, and they took our samples, able to get pictures that look like this, cross-section. BTO, barium titanate, strontium titanate, calcium titanate, stacked like this. So the stacking that we had designed into our recipe is shown in these obtained. So how do they do that? Here's some more images that are of even other materials that are a little finer grained, finer pitched structures here. So one layer of each kind of material before it repeats. System, the scanning transmission electron microscope, and it works in the following way. They take one of our samples and, like a salami, they slice it up really thin. Okay? But even then, it's too thick. So they have to polish it. And they polish it, and make it nice and smooth. Even then, it's way too thick. So then they lay it on its side, and they bring in an ion beam, and they blast away, they sputter away atoms until they basically cut their way through. And when they've cut their way through, and they work their way back a little further, that cut just opened up, they get a thin layer that's only 100 angstroms thick, and they can look through that. And that's what and when they do that, they send their electron, which is a tiny little electron, 1.5, about 1 angstrom big, and as they send it along, sometimes it's scattered by an atom, like these bright atoms right here, and they pick that up on this scattered electron detector, and some not, like in the regions between the atoms, and what you get, what's resulting then is this raster scan across the sample is this picture here, where they are looking at very thin columns of atoms, are the atoms that put in the crystal. So there's another really cool picture. We have been very good in our group in being able to look at that. So let me just, I think we're done here. We better get done. Let me just show you the thing that demonstrates this is a measurement that is with the electronic in this graph, right, asymmetric material on this kind of a measurement. This is the structure here that had built-in symmetry to it. And this one here had built-in asymmetry on one side and built-in asymmetry on the other side. And you can see that this is just a close-up view of this near zero here. This is zero field here, and zero field right there. By doing this stacking, we end up getting material that behaves in the exactly opposite way in this measurement. Here it's got a positive slope, here it's got a negative slope. And so this looks like a good way of doing these kind of things, and we're continuing to work on it. This is the material that has only one of each compound in a unit cell. You can see that we're getting even a bigger slope right now. And so what we're hoping is that we can push this even further and manage to steepen that up. And the steeper we make this, the more responsive. Okay, well, let's skip my conclusions, because I think we've been through everything that I have to say. I want to show you the pictures of my collaborators, the people that have worked together on this. You saw him on the video. He's the guy whose thesis is all of this work and who's been responsible for most of it. Professor Mike Watson has been someone who we've in our measurement of the properties of these materials. There's Jim Zhuo and Hao Chen we had seen earlier, and Xiaofeng Zhai and Michael Vissers, who were also involved in our today's demo down lab. So that's all I have to say. I'd be happy to answer any questions, and I'm sorry if it went a little bit too long, but thanks for listening.